So what is orderability? I'll do it one at a time. So I'm going to work with a co-orientable contact manifold. And I'll say that a contact isotopy phi t is non-negative if, when I pair it with the contact form, the time derivative is non-negative. And I'm going to call this ht of phi tx because I'm going to use that later. So this is what non-negativity means, and I'm going to say that a p-loop is a strictly positive. It's a contact isotopy.
It's like all contact isotopy. Okay.
Yeah. So this is for all t and x. Strictly positive loop, and I assume that it's always based at the identity, which is just a convention. Okay. So what Eli Ashberg and Polterovich did with this concept was they figured out that you could put a partial order on Cont 0 tilde, the universal cover, with the following things. So we're going to say that this is less than this if psi t inverse is non-negative. Okay, and this actually gives a partial order. On the universal cover of the identity component under one condition. So if there do not exist contractible p-loops. Okay. So some examples of where this pops up. So examples of both cases would be, so RP 2D plus 1 with its standard contact structure inherited from the sphere is orderable. So there don't exist such loops. And this was proved in a paper in 2000 using the Givental's nonlinear Maslov index. And to my understanding, they thought that this should lift to the sphere somehow, that there shouldn't be contractible loops of positive contactomorphisms on the sphere. But it turns out that all two subcritical Stein boundaries are non-orderable, which includes standard spheres. And here I'm taking what I mean by a Stein manifold is a complex manifold with an exhausting pluri-subharmonic Morse function. So these are some examples. And the question that I wanted to address was, how does the topology... I'm sorry? So the characterization that I'm giving of a Stein manifold is with an exhausting pluri-subharmonic Morse function. And those things will have critical points of index at most n on a 2n dimensional Stein manifold. At most n minus 2. the highest possible Morse index of a critical point is n minus 2. And this, yeah, this includes including standard contact spheres. S2n plus 1 with a standard. So obviously there's some topology entering in here, and the question I wanted to ask is, to what extent is that somehow flexible or not? So the question is, are all contact structures on the sphere non-orderable? And more generally, so given contact manifold sigma and which contact structure which is non-orderable, does there exist a sigma prime which is orderable? So this is kind of the rigidity of orderability in some sense. And the main result that I wanted to share with you today was that saying that this can be destroyed very easily and in fact locally. Which, so given sigma, which is Liouville fillable, which I'll describe in a second. So I'm assuming just for the sake of not making this vacuous that this is non-orderable. So there exists a different contact structure, which is Liouville fillable. Orderable, and agrees with the original contact structure away from a Darboux ball. And a quick remark on this. So the Liouville fillability doesn't have anything to do with orderability at all. I stated that for technical reasons. So I want to use Fleur homology, and I can use Fleur homology on Liouville fillable contact manifolds. So it's certainly plausible, very likely true, I would say, that this holds in general. And I even forgot, I have to also assume that the dimension of sigma is at least 7 for this to work. But I think that it's very likely that this holds true in general, that you can destroy these things non-orderability locally, but my method of proof doesn't work for the general case. Just any Liouville fillable contact manifold, yeah. So including spheres. So that's the method of proof, is I build it for a sphere first, and then I paste the sphere into wherever I want it. Okay. So 2. So what? Go ahead.
So I was just sort of thinking about this because it sounds like you're basically only making a change inside some small Darboux chart, right, in order to get this context structure.
Mm-hmm.
So is there any way to sort of to consider paths that like fix a point? I mean, instead of considering arbitrary paths of isotope as the context structure, is there any way? Because it sounds kind of like what I'm doing. If I'm taking sort of an arbitrarily small ball and I'm change in here.
Mm-hmm.
Everything else is the same on the outside.
Mm-hmm.
I was just wondering if it's possible, perhaps, to obtain some sort of analogous results to sort of if we restrict to the case where these things, if we restrict to the case that maybe our paths of isotopies are constant on some small, say, constant at a point or constant in some small ball,
Mm-hmm.
then maybe everything becomes orderable, say, for instance. Is that a possibility, or is that just a wild conjecture?
Well,
My question might not be well posed, so don't think too hard.
yeah, I mean, if you fix something, then you're automatically destroying the positivity of it. So I'm not quite sure yet. So yeah, I mean, these things have to be strictly positive in order for this to work. And if you fix something, then yeah, it's 0 there. So the object of study for the technical reasons, is what are called Leoville domains, which are exact, compact, symplectic manifolds. With boundary sigma. And they have to be equipped with what's called a Liouville vector field, which I'll abbreviate LVF. And these have to satisfy, it's basically a convexity condition. So we need X to be transverse to the boundary and pointing outwards. The second condition is the convexity condition, which is that if you take the Lie derivative of omega with respect to the Liouville vector field, it's equal to omega. And the third condition is that, so the negative flow of X exists for all times. So it is complete in that sense. And I'm pretty sure that these overlap.
But if so X is out of point, so it points into some compact region. So why should that not exist for all times?
Yeah, it does.
So 3 doesn't.
Right. 3 was
Not that in the other direction it should exist.
3 was.
Is it not that the condition should be that the outward flow should exist as a flow?
No, because it's compact. I'm just looking at the compact region.
Yeah, but X,
So I used
does
to.
X not point out, so sigma bounds something compact. So if I flow in that direction, I have existence for all time because of compact. So which would be the negative flow.
Right. No. I used to include. I used to not include that in my talk, and I included the third point, which implied that, but then people complained, so I just included both of them. But yes, you're right. That.
Yeah, but is the general not the condition imposed that the flow of that vector field exists for all time?
As long as it's smooth. I don't see that on the board.
No, it could explode out.
But that's the point. But that's the point. Is the first condition says the vector field is outward pointing, and so now backward time everything is going to be moving inward, and the vector field is smooth.
So the third condition there was trivial.
Yes.
Yeah.
The negative flow, but that the positive flow exists for all times is non-trivial.
And false. Not true. It's a compact set. He's not putting on.
Yes, I mean.
Okay, so I thought it was just he has a Liouville manifold and then
Right.
something like this with flows and it just takes a compact region. Okay, good.
Right. No, yes. The third condition is implied by outward pointing, but I included it for the sake of repetition. So the remark I want to make here is that sigma kind of in some sense inherits a contact form. from this setup, which can be defined like this. So I'm going to define my contact form like this. And I'm going to call any such sigma Liouville fillable. I mean Liouville filled. This is a Liouville filling of sigma. Okay. So what I'm going to do at this point is I'm going to form the non-compact completion of this thing by gluing the symplectization of sigma along the boundary. So this is going to be W union along sigma of 1 to infinity cross sigma with the contact form D of lambda union sigma R alpha. So I'm looking at this as a symplectic manifold. Okay, so this is a Leoville manifold, and the reason I'm defining this is because I want to use what's called Rabinowitz Floer homology on this. So this is the technical tool that I use to prove this. Which is defined in greater generality than Leoville fillable. So I think that everything goes through for exact convex symplectic manifolds, but I just stated it for simplicity here. And I'm only going to define the Rabinowitz Floer homology with respect to a p-loop. So I'm going to assume from the outset that I have sigma sitting inside W. I form W hat, and it carries this positive loop of contactomorphisms phi. So given this setup, I can define the Rabinowitz Floer action, or the Rabinowitz action functional A sub phi by this goes from C infinity S1 W hat cross R to R, and it sends a loop along with a real number to, so I pull back the contact form, and it looks exactly like the classic action functional, except that I have this free time component. And what this does is we can view this as a fixed energy version of symplectic homology, if you're familiar with that. So what symplectic homology would do is it would look at periodic orbits of a Hamiltonian. I need to define this too, sorry. So symplectic homology would look at one periodic orbits that occur throughout W hat. What this is going to do is it's going to pick out a hypersurface in W hat and look at periodic orbits of any period at all. So here F sub t, this is defined to be RHT minus 1. So HT is as before, R is the symplectization component, and then I just extend by 0 to the rest of W, or negative 1, sorry.
So it includes orbits of any period. Can they also traverse backwards?
Yep.
Can they be constant?
Yep. Yep. So right away, you get some Morse-Bott issues, because if you pick eta equals 0, you get the entire hypersurface sigma as a critical set. So it's just part of the game, kind of. But it's very useful for studying this sort of thing because it incorporates the fact that the periods are periodic. So some remarks. The first is that the critical set of this is going to be U eta such that U dot is equal to the Hamiltonian vector field times eta. And I also need that f sub eta u of 1 is equal to 0. So that's what you get by looking at the Euler-Lagrange equation for this setup. And so I should point out as well that phi lifts to an exact Hamiltonian symplectomorphism of S sigma via, so I'm going to use a different phi now. And this is going to send r comma x to r over rho tx phi tx. So the second component is sigma, the first component is r, and rho is what you have to modify the contact form by. So rho t of x is equal to, if you put the Rabe vector field in the pullback of alpha here. And so what one immediately sees from this is that this doesn't detect periodic orbits in sigma per se, because yes, it does have to close up in sigma, so it's a periodic orbit of that, but it's also a place where phi eta star of alpha is equal to alpha. So this doesn't detect just periodic orbits, it detects what are called discriminant points. So that's kind of the relation to Givental's nonlinear Maslov index. So that's what he studied when he looked at projective space. So, oh, sorry. Yeah. So the critical set of a sub phi picks up discriminant points. So, i.e., x and eta such that phi sub eta of x is equal to x, and phi eta star of alpha is equal to alpha. And this is tends to cause major headaches later on because this implies that this is not transverse to the diagonal at this point. So in normal Fleur theory, for transversality reasons, you want a transverse intersection with the diagonal. And here you can't have it because of this condition right here. But everything turns out okay using Morse-Bott stuff. Okay. So we're going to do the usual thing at this point. So we build the Rabinowitz Fleur chain complex. So this is equal to the free Z2 module over the critical set graded by the Conley-Zender index. And then RFH star is equal to the homology of this. Assuming that everything's well defined. So that's the proposition at this point is that, yes, it is well defined. And I can state it RFH star sigma W is well defined. In the sense that there are canonical isomorphisms. It does not depend on the completion, so I put the W hat on there for technical reasons. But if this lived inside some other non-compact Liouville manifold, the homologies would agree. If I used some other Hamiltonian function, the homologies would agree as well. Okay, so what I want to do at this point is define growth rates to study these things. So I forget my numbering. Okay. So as Joel said, this picks up, so in this case, so if u comma eta is in crit a phi, I get that the action of u eta is equal to eta. So this is the maxim that the action is equal to the period for Rabinowitz Floer homology. And so I'm going to talk interchangeably about action and period. And so what I can do at this point is I'm not going to look at the entire chain complex. I'm going to truncate it. So I'm going to look at the homology RFH star. And here I'm going to put a negative epsilon here and a C sub n here. So I need that negative epsilon is larger than the first negative critical value. And Cn, this is a sequence. So this is not in the spectrum of A phi, and that Cn diverges. Yep. Yes.
Does RFH star depend on phi?
No. No, it doesn't. I mean, assuming very mild things on phi, but which are satisfied in this case. So for the Rabinowitz Floer homology as it was classically defined, you need that the differential of the function of the Hamiltonian vanished outside a compact set, and that's what you can achieve here by just extending it by you just run off somewhere and then you. So the here it is right here. So this condition right here tells you that the R value. Oh, you probably can't see that, can you? Sorry. It says f eta of u of 1 is equal to 0, which means that the R component of any of these critical points, all of them are contained in a compact set. So you can just extend the Hamiltonian by a constant after that, and you don't lose anything at all. Okay. So yes, so I'm killing all of the critical points with negative action values, and it's probably overkill in any sense. But the reason is that RFH star negative epsilon to infinity, this is isomorphic to the symplectic homology of W hat. And so this implies that you get all the theorems. So Rabinowitz Floer homology is certainly not as developed a field as symplectic homology. So a lot of the nice technical results that have been proved just you get for free via this isomorphism. Okay. So what I'm going to do is I'm going to form a sequence A of n, which I'm going to define to be the rank. So all of these have inclusion homomorphisms. So I'm going to look at the rank of this map right here. So this is going to include into here. And then I'm going to define gamma plus to be the log limit of this. So this is the lim sup as n goes to infinity, log of an divided by the log of n. And the reason that I'm using this is because this precisely tells you if this is equal to 1, you have linear growth for the homology. And what you get for a p-loop is you get precisely linear growth of the chain complex. And so that's going to allow me to complete the argument in a little bit. Okay. So the proposition at this point is gamma plus of sigma w is well defined as written. So what I mean here is that this does not depend on the completion, and it does not depend on the Hamiltonian. So certainly the chain complex here, if I truncate the action value, that will certainly depend on the Hamiltonian. But the growth rate of the homology does not. And so this is due to a result of Mark McLean, which says for a symplectic homology that gamma plus is a Leoville invariant. So if I take Leoville domains and a Leoville isotopy between them, gamma plus is an invariant of this. Okay, so that's the bad part. So now the good part. So the upshot of all this is the following proposition, which says that if gamma plus, so if sigma admits a p loop, gamma plus is less than or equal to 1, which by itself is not that interesting until you consider the fact that this is stated for any filling, W. So the contrapositive of this states that if there exists some filling W with gamma plus sigma W greater than 1, sigma is orderable. Is it clear, the implication as I've written it? So orderability does not depend on the filling, of course. So all that you need to do to verify that something is orderable is find some filling which has the growth rate bigger than 1. So this would be superlinear growth. So an example of this, which doesn't not an exact analog, but for contractible p loops. So I'm stating this for all p loops. My advisor, along with Will Mary, proved that the Rabinowitz Fleur homology vanishes identically. And what you can do here is, so you can show that, so I guess this would not be hard in general to show, but you can show that S1 is orderable this way, because even though if you fill S1 in by a disk, all of these things vanish. If you fill S1 in, so with a punctured torus, then all of the periodic orbits live in disjoint different homotopy classes. And so the Rabinowitz Fleur homology can't vanish, and so you get that this thing is orderable. So I'm going to give you kind of two proofs of this, why this is true. So the kind of satisfying proof of this and by satisfying I mean completely intuitive, is why doesn't the torus admit a p metric? And what I mean by a p metric here is it would induce a positive loop of contactomorphisms on the unit cotangent bundle. So the reason is, so that's the Q, here's the A. You can group the homotopy classes of geodesics on the torus like this, A to the P, B to the Q. And there does not exist, so given J and K and Z, there exists P and Q such that, well, A to the P, B to the Q does not equal A to the J, B to the K to the N. So that you're getting qualitatively new information from these new geodesics. And what that means is that they can't have come from a loop. So the loop only contains information about itself and its iterates. You can't get anything new out of it. Okay, so that's the heuristic proof for why this is true. And the actual proof is shorter, in fact. So if you do it right, so what you have to do is you have to do the Morse-Bott case here. So if you do Morse-Bott right, RFC star grows linearly. And the rank of the image of the homology into some other vector space is, of course, bounded by the dimension of this. So this means that RFH star grows at most linearly. So this is assuming, of course, that you have a p-loop to start with. So the p-loop only contains information about its own closed orbits, and it can't give you more information than that. Okay.
What does it mean, gives you information?
So what I mean is that if you look at the torus and you look at the homotopy classes of geodesics on it, you're getting, by increasing the length of the geodesic, you're getting new homotopy classes that aren't contained as iterates of previous homotopy classes. That's what I mean by new information. So there's new periodic orbits that aren't iterates of previous ones that are popping up. And so that's what has to happen if that gamma plus is bigger than 1. You have to be getting new information somehow. Okay. So from there, the strategy for getting an orderable context structure in any Leoville fillable manifold goes like this. So what you're going to do is we're going to do n connect some surgery. So we're going to do W connect sum with B tilde. So B tilde is going to be a non-standard ball. With gamma plus of B tilde at least 2. And the way that you get this is that, so there are a couple ingredients here. So the symplectic homology of the n-connect sum is isomorphic to the direct sum. Here. So I could have started with 0 symplectic homology, and then by gluing in this ball, I'm going to have crazy symplectic homology. So that's basically what we're doing. We're twisting it around so much inside that ball that we're getting at least quadratic growth for the homology. So this is due to a special case of Chili-Bock's theorem, which states that symplectic homology doesn't change under subcritical surgery, and this is subcritical surgery. So I need this, and then I also need to construct B tilde. And this is somewhat complicated and tedious, but it follows ideas of Paul Seidel and Mark MacLean. So what Paul Seidel constructed was an affine surface with non-vanishing symplectic homology. And so what you can do is you can do, so I'll call that thing A. And what I'll do is I'll attach the cotangent bundle of the torus, the disk bundle of that. And so what this is going to give me is that this thing is going to have at least quadratic growth in the Rabinowitz Floer homology. And then I do subcritical surgery. To make it topologically a ball. And smoothly, I mean even smoothly, but so you just do Weinstein surgery along the way to kill the fundamental class given to you by each of the circles in here. The symplectic homology doesn't change by Chili-Box theorem, and then you get a ball with quadratic growth for the homology. And so that gives you quadratic growth for the symplectic homology of this thing, and that's an orderable context structure. So this implies that W, the boundary of this, is diffeomorphic to sigma and is orderable with the induced Leoville context structure. Okay. So some applications of this. That I didn't first think of when I was writing this because I hadn't considered these things at all. But the important thing is that this thing admits no loops, positive loops of contactomorphisms at all. When orderability was first introduced, it had to do with contractible loops. And so what this gives you is it gives a partial order on Cont 0. So you don't have to lift it to the universal cover to get the partial order. And if you combine this with a result of Sondon, which uses orderability to get bi-invariant metrics on Cont 0 tilde, it gives a bi-invariant metric. So this is a z-valued bi-invariant metric. On Cont 0. Okay. All right, so some generalizations of this that I've been considering. Focus mainly on the following questions. So, is there a Legendrian obstruction? So in the two subcritical case, you don't have any Legendrians that are worth anything, basically. And so if you consider this from this perspective, there's no Legendrian obstruction to the existence of a contractible loop of positive contactomorphisms. in the case where it's orderable, is it necessarily because there's a Legendrian obstruction? So the example would be so given a Stein manifold, I'm going to call this set so this is the set of all Legendrians arising as regular level sets intersected with unstable manifolds of a plurisubharmonic Morse function f. So the question is, can we define a partial order on this set right here? And there are a couple ways of going about it, but the easiest way is what you would do is you would fix one Legendrian lambda naught, and you would look at the set of so phi t such that phi t is a Legendrian isotopy. Starting at lambda naught. So you can define the same idea of a partial order here. So is this a partial order? And a quick observation says, oh, I can't use that one. A quick observation shows you that if there exists a single Legendrian such that this does not admit contractible p-loops of Legendrian isotopies, then sigma is orderable. Because if sigma were not orderable, it would admit a contractible p-loop, which of course gives you a contractible p-loop of Legendrian isotopies if you restrict attention just to the Legendrian. And the question is, does the converse hold? Namely, given an orderable sigma, does there exist an orderable Legendrian inside it? And kind of the line of reasoning behind this is goes kind of along the lines of reasoning of the exact triangles between symplectic homology and wrapped Fleur homology, if you're familiar with that. So you can consider both the relative case and the absolute case at the same time and look at the interaction between them. And if you follow this line of reasoning to its conclusion, what this tells you is that if there is indeed a Legendrian obstruction to p-loops, so this would be another question. So if the Legendrian obstruction exists, then for a Stein, for a one critical Stein manifold, the obstruction vanishes. Because what I should have but neglected to write over here is that this can't be just any unstable manifold because the dimensions don't add up. This has to be an unstable manifold of a critical point of index exactly n in order to give you the right dimensions. So if you have a one subcritical Stein manifold, there are no such Legendrians. So this would imply that one subcritical implies non-orderable. Which, unless I'm mistaken, is still open. I was going to say something else at this point, but now I'm forgetting it. Oh, okay. And so then the other question would be, if all Legendrians are non-orderable, so if this little conjecture is false, so if all Legendrians are non-orderable and sigma itself is orderable, so must the wrapped Fleur homology so must you have two different Legendrians which are interacting in some strange way? So that the way that you could conceivably go about a proof to this thing is, so for two subcritical Stein manifolds, you can displace them, and that's what gives you this notion of there's a way to get a positive p-loop out of that. And so what one could conceivably do for a Stein manifold, at least, is you look at everything except for the ascending manifolds of an index n critical point. And conceivably, you get a p-loop on that. And then you get a p-loop on the other side, but it's 0 on the ascending manifold. And the question is, can you graft these things across it? And the only obstruction to this would be if there were some sort of interaction of this shape right here. So this is kind of idle speculation at this point, but I thought that these were interesting questions related to this. Thank you.
Thank you very much. It's nice.